Hello, hello. So now we are doing number of distinct islands part two. And what is this question? You are given a M by N binary matrix grid. An island is a group of ones representing land connected four directionally, one horizontal or vertical. You may assume all four edges of the grid are surrounded by water. An island is considered to be same as another if they have same shape or have same shape after rotation or reflection. Return the number of distinct islands. My God, this. I don't even know what to do. Like it's a scary problem. It's a very scary problem. But let's see what we can do. So these two should be same because they are like a reflection to each. Are they a reflection? Mm. They are like a rotation, like a 180 degrees rotation. Hmm. Hmm. I have no clue. See, one thing that comes to my mind is somehow chart this out, chart all the islands out, and check which of them are non-distinct. Like, how would you do that check? So I can use the BFS to find out the edge element. So this will be an edge element, the first element. Uh, I find this element, I do a BFS, DFS, let's say I do a DFS, and I find out the shape of this. So the shape of this will be defined by this element. If it ended here, so it would be this element and this element. Or if it ends here, so this element and this element. So all those three are wherever the graph can't move anywhere, I store that in a shape. Okay. Topological sort works. I was thinking somewhere on the line of topological sort, but it works on TAGs, directed acyclic graphs. There is no direction and it is cyclic. Uh, directed. Hmm. Let's use some hints. Oh, there are no hints. Companies, which companies are? Amazon, Meta. Ah, my brain does not work. Yeah. Canonical hash. It's a system of number of distinct problems. We determine the local coordinates of each other. And therefore, afterwards, we rotate and reflect the coordinates amount. That was my idea. But how to do that? We'll have to watch the video on this. It's not easy to cross.
Traversal and the DFS traversal, but where will it be applied? So you're going to do a bunch of problems, and this video is going to be about the first problem, number of connected components. So let me explain you the problem. So what does the problem state? The problem states you'll be given a grid of size n cross m, where n is the not touched, I'm not visited. You have to do a starting point as equal to 0. Now you're this, and perfect. This 2 plus 1. So they might be crossing boundaries. So this is how you can easily use the BFS algorithm in something like a matrix. What about the time complexity? Everyone is marked as one. So the BFS will travel like n square nodes. If everyone is marked as one, the BFS will travel like n square into 9.
Ah, that's still not helpful. That's not- Okay, so let's just go and see what they are doing. Just try to replicate that. Let's start clear. Let's go so clear. And let's move to eyes. And size. Okay. Now we are making a Boolean vector. Seen. I prefer visited, but it's okay. Seen is equals to vector bool of size n, comma, vector bool of size n, comma, 0. Cool. What is hash? Basically, unordered set. Shapes for all the rows, for all the columns, shape, excuse, shape is equals to new vector int. And the explore function, if it's in bounds, then and if it's one and if it's not seen, then we make scene true, save dot push. Integrate. See. Okay, we have this. Let's see if it's working. It's only giving correct because now if shape is be back. So this is what we have done till now. We have basically done a DFS and found the shape of the element. This is like basic, it's proper. Is it a PFS or DFS? Yeah, it is a DFS. So it's not that difficult. And my idea was different, a little different, where I wanted to store only the last element. But instead of that, they are storing all the elements that are in the shape, which is okay. Uh, so whenever they find it is a one, they create a shape. They do whenever see this is one, so they'll store this and they'll check its neighbors. Then they'll find this, so they store this, check its neighbors. They don't find them to be one, so this is stored. Now they come this side, they store this, check its neighbors, and proper DFS. This also proper DFS will be done. So that's not an issue. Now the main thing that boggled me was this canonical shape. How would I do that? And this is what they are. Uh, like this is why I had to look at the answer. So let's try to figure it out. Let's write this on our own only. Shape not there is a empty function because there is an empty function for stacks and queues. So I wanted to check if it is the same for push. Canonical shape, canonical of shape. This is the hard part. Okay, returns a string. Let's write it on our own properly. String canonical takes a vector of int shape string answer int left is close to n plus m plus n. Ah, I don't understand any of these. Why this left right now? Do they have a logic for canonical shape? Bottom left most can coordinate is 0, comma 0 after it. Ah, okay. I don't understand any of this. How do we form a canonical shape? That is the.
Hey, hey, well, hopefully. But I keep on saying it, but it's still true, which is that I gotta, one day, don't give islands. This is a very tricky one. I haven't done this one yet, obviously only because, yeah.
I think there are not a lot of videos on this, which I understand. It's a premium question. We'll have to look into this only and try to understand this. How are they using the lift? Oh, mm, was- Let's try to write this out and then see if figure out figure it out. Vector int uh, out of size int if of shape dot size of size k comma xs of size k comma ys of size k. Cool. For c and c is equal to 0, c smaller than a, c plus plus for all the eight possible combination. In t is equals to 0. I don't know what t does. For z in shape, every element of the shape, okay, shape is an integer. We'll get the row and column using this. Cool. Problem setter seems to be very lazy, or the person that has written this answer, editorial. What is C? Okay, this seems good. Okay, we are transforming all the uh, parameters into this eight parameters, which is okay. I understand this. So if less than one equals to one, x uh because 0, 1 is x. After that, 2, 3 is minus x. Uh, then 4, 5 X will become Y, and y 6 minus y. Cool, cool, cool. I understand this. This is good. Okay. So for every time t is equals to 0 first, it creates, it goes through all the elements in the shape and it creates the xs and xy for c is equals to 0. Next, some value mx and then y. Yes, we find the left element, bottom left element using this. Cool. In this canonical. And then okay, we find the bottom left element and then make a hash out of it. And find the smallest string. Java stuff. We'll go through this once again if this works out. It does not. Mm, 1, 2, 3, one shape. 1, 2, 3, other shape. Yeah. Huh? There are two shapes. Uh, why is this a problem? How will this look? Can we draw V? Hmm. So, so this is one shape. This is another. These two are the same. So there are two shapes. Now let's try to use this as case and debug it. So after exploration, I should have shape. Shape is 0, 5, 1. Uh, so 0 will be 0, 0. 5 will be this one. So 1, 2, 3, 4, 5 plus 0. Because 1 into 5 in plus 0. And 0 into 5 plus 1. This is good. Exploration is correct. It is not empty. Let's go inside canonical and see how it works. Good actually that we got a chance. Answer K lift is 9. We are out and everything. T is equals to 0, T is equals to 0, Z in shape. We get the XY position. Now x6 of T of 0. Okay, 0, 0. Cool. Because C is equals to 0. Basically 0, 5, 1. 1 mesh. Be right back. Ah, okay, yes. Okay, okay, okay. 1 0. That is cool. We have all the sides. Now minimum x, find the bottom left, top left. Find the minimum x, okay, and find the minimum y. Now this is the canonical transformation. This is the problem. And the date plus is equals to 2 ring of x. Oi. Somebody has better solutions. Okay. Union find? How will you do union find in this? Bruh. For all elements, we make a hash out of it. Interesting. Besides. It is a hashing question, basically. We have to find the canonical form. We have to hash it. Whoever can get the best way to hash it wins this problem, which is good. This guy graph bipartite seems like a bad word. Seems like apartheid. Bipartite. Oh my God. I'm fucking tired. A graph bipartite. There's an undirected graph with n nodes where each node is numbered 0 to n minus 1. Cool. Zero based indexing. You are given a 2D array graph where graph of u is an array of nodes that u is adjacent to. Okay. So 0 is adjacent to 2, 3, and 1, and like that. We are given an adjacency list. More formally, there is an undirected edge between. Okay. There are no self edges. Cool. There are no parallel edges. Okay, so Okay, cool. Uh, if V is in graph of U, then U is in graph of V. The graph is undirected. The graph may not be connected, meaning there are two. Cool. A graph of bipartite if the nodes can be partitioned into two independent sets ANV such that every edge in the graph connects the node. A graph is bipartite if nodes can be partitioned into two independent sets, okay, A and B, such that every edge in the graph connects a node in set A and a node in set B. Okay. I think we can. Yeah. One, three. Okay, so they should not connect in each other. If you do 1, 3, then 0 and 2 connect each other. Should only connect to the other graph. Let's take 5 nodes. Is this bipartite? Yes. Is this bipartite? Yes. We can divide this. Or every edge connects a node and one. If the nodes can be partitioned into two independent sets, okay, such that every edge in the graph connects a node in set A and node in set B. Okay. So is this by let's see if this is bipartite. Yes, because every edge in this set A connects to B. If we can divide it this way, we can divide it this way, we can divide it this way, we can divide it this way. That is correct. Let's add this. We can divide it here. It will not be bipartite. If we divide it here, then it will be bipartite because every edge from A will connect to B, B will connect to A. We can divide it here. If we divide it here, it will not be bipartite. If we divide it here, it will not be bipartite. So let's take 0. Everything that connects to it should be in other set. 1 and 3 should be in set B. Okay, let's add these two. This should be in set B. Now we come to 1. Okay, 1 is in set B. 1 is already in set B. So 0 should be in set A, which there is. 2 should be in set A, which there is. Now 2 will be in set A. So 1 should go in set B. 3 should go in set B. I think this could be easily done. If I make two sets, add 0 to that set, and the all the nodes connected. So here I add 1, 2, 3 into set B. I come to 1. I add 0 to set A. I add 2 to set A. Okay. Then I come to this. I find 2 to be in both of the sets, which is not possible. So it gives a false. Or if I don't check it here also, I can check at the end if the sum of both sets should be smaller than n. So, like should be not be equal or greater than n. So yeah, I think this is easy. Set int a comma b. A dot in place 0. Okay, for all the elements, if a dot find I not equals to end a dot end. If it is in set A, then B for x in graph of I, B dot in place x auto. Else A dot in place. Cool. And at the end, return A dot size plus p dot size and is equals to 1 dot size is equals to n. Should work, I think. Wrong answer. Smaller than equals to n. How many are there? 1, 2, 3, 4, 5. Okay. 0, 1, 2, 3, 4. 0 is connected to 4. 0 is connected to 4. 1 is not connected to anything. 2 and 3 are connected to 4. 2 and 3 are connected to 4. Four is connected. Yup. This works out. And there is a set. This should be true. Yep. So I have 0 in one A, 4. So I think I will have to do DFS. Yes, I will have to do DFS also. If st instead of set, I can also add markers. Ah, done. I saw there is one viewer, so I thought let's just do this for you, my guy. I am very tired. No. Okay, let's try this out. Uh, okay. So we come to 0, we find it is not st of 0 dot find. It's not in any of those sets. So we enter the find I not is equals to n st dot n. If it is not in both of the sets, st dot 1 dot find. Better we keep a visited array. Visited vector int visited of size n all are -1. Okay. If visitor of I is equals to -1, in that case, what we do, we add it into set A. Visitor of I is equals to set A, let's say 0. And then we do a DFS on it. So DFS of I. Okay. Now we'll have a bool function DFS which will take int I graph we can store above and this dot graph is equals to graph. Okay. And now we do a DFS. So for all the elements of I, also we add 0, comma in set. Okay. It's in I is in set 0 for so set plus 1 mod 2. We can remove this for auto x in graph of I for all the elements that are neighbors to it. What we do, if not visited of x, we just visit it. So what we do is visited of x. Let's do this here. Visited of I is equals to set. So BFS of x, comma set plus 1 mod 2. If visited of x is equals to still -1 if we have not visited it. If it has been visited, then No. Return 0, same thing. I comma 0. Return visitor. Visitor equals to vector int of size n, comma, all or minus 1. And this works. This should submit 100%. My God, I've done this very well. Like, could have done better on memory. Memory complexity is often of V. I meant like V, and this is also V plus E. Uh, how can we do better? Can we do, like, is there any way we can do it better? I don't think so. Can we increase the memory better? But can we utilize the memory better? I don't think so. I think this is it. Let's see what other people have done. BFS. This is also good. Similar approach in a BFS fashion. Both BFS and DFS. It's a BFS. Yeah, my auxiliary space would have been taken. That's why I'm not doing well on memory because I'm taking stack spaces. There's an auxiliary stack which is taking space. But it's okay. I can convert this into a BFS solution if I want. It's okay. I know how to do this. Cycle detection in a directed graph. No one is watching. I'm taking a risk.